This is section 9.4, hypothesis testing for means. In chapters 7 and 9, we learned that confidence intervals are types of statistical inference that can be used to estimate parameters based on the results of a sample. The margin of error for these intervals allows us to quantify how confident we were in the estimates. Similar to chapter 8, today we are going to use hypothesis tests to make decisions about whether it's likely that a population parameter is equal to a hypothesized value. So in this chapter 9, section 9.4, we're looking at hypothesis tests specifically for means. So in each of the following cases, a person is interested in making a decision about the value of a population parameter. So scenario 1, a researcher is interested in testing whether the cost of college has increased over the past year. A researcher is interested in testing whether vegetarians' cholesterol levels are lower than the US average. And the third scenario, a consumer would like to know if the advertised weight of a candy bar is correct. So all of these are very similar, but yet they have some differences, and we're going to look at that now. So hypothesis testing is another type of statistical inference. So in this class, we learn about confidence intervals and we learn about hypothesis testing. Hypothesis testing allows us to choose between two claims made about the population parameter. So this is important. The claim about the population parameter. The first one we're looking at, the cost of college has either increased or not changed. We're looking to see, is the cost of college greater or is it still the same? Vegetarians' cholesterol levels are either lower or still the same. In this case, we're looking for whether they're lower than the average, US average. And the last statement, the advertised weight of a candy bar is either correct or not correct. So this is a case where we're looking to see if the population parameter is equal to a certain amount or not. So all of these scenarios would be made based on just one sample statistic. A person would take one sample, calculate a mean, and then have to make an inference based on that one statistic. Given that statistics vary from sample to sample, the decisions we make regarding these parameters are uncertain. So we don't know if what we're observing is because the true parameter was wrong or if it was just, variation in the sample. So how do we make these decisions? How do we know if we've made the right decision? What's the probability that we make the wrong decision? So hypothesis testing provides us a method for making these decisions and allowing us to control the probability of making certain types of mistakes. For example, the chance that we make the wrong decision. Let's use an example to illustrate the 4 steps of a hypothesis test. How can we test whether the advertised weight for a particular candy bar is correct? So that's the question that we're interested in. The weight, whether the weight of a candy bar, the advertised weight for the candy bar is correct. So on the next page, we see step 1. First, we want to state our hypothesis about the population parameter. We always are talking about the population parameter when we're stating our hypothesis. So we start with the null hypothesis, which is denoted by H0, which is a status quo. It's like what we already believe. It's the viewpoint that's out there about the population parameter. Okay, and it states that the parameter of interest is equal to some specified value. So the advertised weight is 2 ounces. That's in words, sorry. The advertised weight 2 ounces is correct. So now using symbols, that's saying that mu, the population parameter, is actually equal to 2 ounces. And our book talks about what mu is equal to under the null hypothesis. So sometimes we see that like that's called mu naught. Then we state the alternative hypothesis denoted by HA, which is the alternative to the null. The change in population parameter that the researcher is hoping is true. So this researcher's question, and this is where we find this alternative hypothesis, said is wanting to know whether the advertised weight is not correct. Okay, so in this case, we're going to say that mu is not equal to 2. So we're either equal to 2 or not equal to 2. These hypotheses must be specified before the sample data are collected. Okay, so you have your plan before you've even looked at any data, before you've even collected any data. So similar to chapter 8, we have the following options for our hypotheses. We can have a two-sided, and this is the one that we're first looking at, where our null says that we're equal to mu naught, and our alternative says we're not equal to mu naught, which means that we're going to be looking in both tails when we're working with this one, and that's why it's two-sided. The other two options are both one-sided. One is to the left, where the alternative hypothesis is less than mu naught, and then one is to the right, where the alternative hypothesis says that mu is greater than mu naught. So a significance test is designed to assess the strength of evidence against the null hypothesis, and we will assume that the null hypothesis is true until we collect enough evidence to suggest otherwise. So this is really a nice way of thinking about this. Remember that the hypothesis test is similar to how our justice system works, and we're assuming innocence, which in this case is the null hypothesis, until there is enough evidence to conclude otherwise. Okay, so we assume the null, and then if we're able to show that there's enough evidence, and then we would say that we would reject the null hypothesis. All right, so let's go continue on. Step 2, we need to determine how you will use data to make your decision and choose a significance level. So we'll talk a little bit more about our significance level at the end. But for right now, our significance level that we're choosing is going to be alpha is equal to 0.05. We use alpha to denote the significance level. Assuming the advertised weight is correct, we know that our sample of candy bars will typically have means close to mu, mu not equal to 2, give or take a little variability. So how much variability do we expect? We can use the central limit theorem to create a sampling distribution for the sample mean weights when n is equal to 4 candy bars, if the following conditions are satisfied. So we're going to check our central limit theorem conditions, and then we're going to, if we can use the central limit theorem, we can create a sampling distribution so we have an idea of what we can expect when we have a sample of 4 candy bars. So condition number 1 is the sample random and is each observation independent. So yes, we're taking a random sample of candy bars and they're independent from each other. Is the sample large enough? So our sample size n equals 4. That is not large enough, but it's probably safe to assume that the population distribution is normal in this case. So this condition is also met. And is the population large enough? So is n times 10 less than our total, oops, excuse me, try this again. So is our total population greater than n times 10? And so that's equal to 40. yes, there's probably way more than 40 candy bars in the whole population. So since the three conditions are met, we can create a model for the sampling distribution for X bar. Remember, we're assuming the advertised weight is correct until we have evidence to suggest otherwise. We will need the standard deviation of our sample to calculate the estimated standard error. So our standard deviation of our sample is given to us right here. So using the central limit theorem, we would say that the sampling distribution for X bar is approximately normal. With mean, it's going to be centered at our our mu naught, which is 2, and it's going to have an estimated standard error that we have to calculate. We're going to use the formula here. So S is our sample standard deviation, so 0.03651 divided by the square root of our sample size, which is 4. And that gives us 0.018255. Okay. So we say that our sampling distribution is approximately normal with it's centered at 2 and has a standard deviation of standard error of 0.081. Okay, so now we can sketch the sampling distribution, which is always helpful to have a good look at what's going on. It's centered at 2, and we can fill in the mean +1 standard deviation, +2, -2, and so on. Okay, so the weights of the candy bars in our sample are, and here they are, 1.98, 1.9, 1.96, and 1.92. So now we can calculate our sample mean, which we would call X bar, and that comes out to be 1.94. So I always like to just take a second to look to see where does 1.94, where does my sample mean fall on this distribution of sample means that I drew up here. And it looks like it's going to fall way out here in one of my tails. So that's just going to keep that in the back of my mind, that when it's out in the tail, that's an unlikely thing to see. So we just want to keep that so that we know when we're doing our calculations, we're on the right track. So the next step is to calculate our test statistic. We are going to be using the t-test. And remember, that's different from the z-test statistic, because instead of using the standard normal, we're using the t-distribution, which has slightly thicker tails. Other than that, they're very similar. So our t-test statistic is given to us right here, and we are going to calculate that. So we need to do t is equal to our X bar, which is 1.94, minus mu under the null hypothesis, which is 2, over our estimated standard error, which I'm going to round to 0.018. And this gives us a negative 3.33. So remember, the t-test is really saying how many standard errors away is our observed mean, which was 1.94, from our from the mu naught, which was 2. So it's pretty far away. It's negative 3.33 standard errors away. So now the next step is to calculate the probability of getting a sample result this extreme or more. And this is called our p-value. That's the probability of seeing a sample this extreme or more extreme. The p-value is the probability, assuming the null hypothesis to be true, of obtaining a test statistic that is at least as extreme as the one actually observed. extreme means in the direction of the alternative hypothesis. So in other words, further out into the tails of the alternative hypothesis. Since our alternative hypothesis did not specify a direction, we need to look at the sample results that are as extreme as the one we found in both tails. So just sliding back up here, we're talking about also this tail. Oops, let me do that in red. This tail over here, okay? We're talking about both tails. We're going to have to look at the probability of observing something in either one of those tails. So we can find this estimate of the p-value from the t-distribution critical values table on the next page, or find an exact value using technology, which is really what's most often done is use technology, but it's worth looking at the table. So first we'll do it using the table, and then I'll show you on technology. So on your next page, you have the t-distribution critical value table. And in our problem, our degrees of freedom, well, our degrees of freedom is always equal to n minus 1. In our problem, that's 4 minus 1. So the degrees of freedom is 3. We calculated a t-statistic of negative 3.33. And it only gives us the positive ones in this table. So we're thinking about 3.33. And so if we go across in this row here of degrees of freedom equaling 3, we're looking at, I guess I'll just outline this row. We're looking at the number 3.33. And that's going to be between these two numbers, a little bit closer to this one here, right? 3.18 versus 4.5, but it is between these two. So the probability you read off from this little number right here. So because our t-statistic was equal to 3.33, we're like, okay, here's this is the number we're matching it closest to. So the probability is about 0.025. I'm going to flip back a page. So because we're doing two tails, we actually have to multiply that probability by 2. If we were only looking at greater than or less than, then we would just use that because it would give us a probability of being a one tail. But because our alternative hypothesis said that mu was not equal to 2, the not equal part is telling us that we have two tails to look at. And so we have to multiply these by 2, and we get about 0.05. So we know that the p-value is close to 0.05, but it's not going to be quite 0.05 because we're somewhere between these two values. This other one, you can see that the probability is 0.01. So going back, if we thought about the 2 times 0.01, we'd get equal to 0.02. So the probability is somewhere between 0.02 and 0.05, probably closer to 0.05. But anyway, that just gives you an estimate of the p-value when you use the table. Okay, so on the next page, you can see the StatCrunch output right here. I'm going to switch over to StatCrunch quickly and show you that I have the 4 candy bars weights here. If you go to Stat, T-statistics, one sample with data, I want variable 1. I'm doing a hypothesis test to see if my mu is equal to 2. My alternative hypothesis is that it's not equal to, so I'm telling it that that's what my alternative hypothesis is. And I'm going to just put the p-value plot on because it's nice to look at. Okay, we compute, and here is our hypothesis test output. I double check that my null is equal to 2, mu equals to 2, my alternative mu not equal to 2. Here is my sample mean. That's what we calculated by hand. That's X bar. Here's my estimated standard error, same as what we calculated. Now they don't round when they continue calculating their t-statistic, and we did round, but it's close to negative 0.33 that we got. And here is the actual p-value calculated using technology is 0.046. So that is very close to 0.05. And finally, the picture, which I like to look at. So you can see that the red is what the p-value is telling you. What's the probability of seeing an X-bar that is in either of these red areas? And it tells you that that probability is 0.046. Pretty unlikely. So here I am back on our notes, and we have the StatCrunch output right here for you. And it says to mark the location of your t-statistic on the following t-distribution. So we have the 3.33. So we're looking at the probability of seeing something out in these tails. And then the next part of this says to interpret your results. So we always have a choice between these two decisions when we're interpreting the results of a hypothesis test. We can reject the null hypothesis. We have evidence that suggests that the advertised weight is not correct, or we don't reject the null hypothesis. We don't have enough evidence to suggest the advertised weight is correct. So those are the two choices with every hypothesis test. You either reject the null hypothesis or you do not reject the null hypothesis. We have to be very careful about our wording, okay? Because we cannot say that mu is equal to 2. We have not proven that mu is exactly equal to 2. All we're saying is that we wouldn't have enough evidence to say that it's not equal to 2. And that's a very careful line that you don't want to write wrong when you're writing up your results. So these decisions are typically based on how small our p-value is. So remember, our p-value from the previous page, or I think from above, is 0.0462. The smaller the p-value, the stronger our evidence is against the null hypothesis. So the smaller the p-value, the less the probability of just seeing that that sample mean by chance. And so it's pretty, gives us evidence to reject the null hypothesis. So the way you make your decision is that if your p-value is less than your significance level, so remember we chose a significance level at the very beginning of 0.05, we reject the null hypothesis. So in this case, our p-value is in fact less than our significance level, and we will reject the null hypothesis. So what we're saying is that our results are statistically significant. In other words, the X-bar we saw is far enough away from our null hypothesis of mu equals 2 that we don't think it happened by chance alone. So this is significant, and we're rejecting the null hypothesis. Is it possible that we could reject the null hypothesis even though the advertised weight is correct? And what is the probability of making this mistake? So this is one type of error that could happen with a hypothesis test. So yes, it is possible that we would reject the null hypothesis even though it is actually correct. And the probability that we make this mistake is our significance level. It's 0.05. And so we pick a significance level, you know, based on what the probability of this mistake we want to make. So what is the probability that we make this type of mistake? And it's going to be 0.05 because our significance level is 0.05. Is it possible that we could fail to reject the null hypothesis even though the advertised weight is not correct? Yes, that's also another type of mistake that's possible with the hypothesis test. And we're not going to quantify that in this class. But so those are two different types of mistakes you can have. All right, so now let's just do a summary of our hypothesis test. Key points about a one-sample t-test. It's a procedure for choosing between two hypotheses about the true value of a single population mean. The test statistic that you're going to use is a t-test. And it compares the sample mean to the hypothesized population mean under the null hypothesis. The estimated standard error is given with this formula that we've been using. It gives us a way of making decisions about the population parameter based on our estimate from a sample, while knowing the probability that we will incorrectly reject the null hypothesis. This test procedure only works if the sample size is large enough and the sample is randomly selected. In other words, we also need to have the central limit theorem conditions met. Small p-values indicate an extreme test statistic, and extreme test statistics means something unusual or that we see something that's statistically significant. How extreme would the mean weight of your sample for 4 candy bars have to be to convince you that the advertised weight is incorrect? So probably that would need to be about 2 standard deviations away from the mean in order for us to think that's incorrect. And the two types of errors that can be made are mistake 1, we reject the null hypothesis when it's true. The probability of this happening is indicated by the significance level. The smaller we set the probability, the higher probability of making mistake 2. So you have to think of these two mistakes as kind of a balancing point, and you don't really want to make either mistake, but there's always a probability. And so if you try to eliminate mistake 1, then it makes mistake 2 more likely to happen. And if you try to eliminate mistake 2, it makes mistake 1 more likely to happen. So it's kind of a fine balancing point. Mistake 2 is that we fail to reject the null hypothesis when it is wrong. And which mistake is worse? It depends on the study. In the candy bar case, it's not necessarily as easy to think about, but you know, if you're trying to do some kind of test about tumor size and you know, you have to make some kind of cutoff for tumor size and maybe whether it's cancerous or not, you can see where having a false positive or failing to reject when it's wrong, those two things would be very meaningful in certain situations where you don't want to make one of the mistakes. So you would set your significance level appropriate for that specific case. And statistically significant results tell us that our sample results are so extreme compared to what we expected if the null hypothesis were true that it cannot be convincingly explained by chance. Keep in mind that when you state your conclusion to a hypothesis test, you are not proving that the population mean is or is not equal to a particular value. If something is proved, it's absolute and without any doubt true. However, we cannot be absolutely certain about our results since they come from a random sample. This is why we limit ourselves to one of the two following conclusions. We either reject the null hypothesis or we fail to reject the null hypothesis. We are choosing the conclusion that seems most likely given our sample data. We do not want to use words like proved, but rather we would say demonstrated or showed or suggested. Those are the words you want to use. Let's revisit our hypothesis test we just did. Our sample mean was 1.94 and our sample standard deviation was 0.03651. The following are the results were done in StatCrunch, as we saw. And now we're seeing the results. So this is the one we just saw. And here are our 95% confidence interval results. So if we look at the confidence interval, we can see that the interval does not contain the number 2. So 2 ounces, not an interval. And our hypothesis test results give us a p-value that say we would reject null hypothesis. Let's do it like that, reject H naught. So both of these results are very similar in the fact that they both say that, that it's unlikely that mu equals 2, given our sample, that the actual, given our sample. So remember that the confidence intervals are used to answer questions, such as what is the value of this parameter, where a hypothesis test is used to answer the question, are the data consistent with the parameter being one particular value? Might the parameter be something else? Okay, and that wraps up section 9.4.